So my name's Jim Thomas and I'm a professor of bioinorganic chemistry. I'm kind of in the interface between coordination chemistry and biology. We're interested a little bit in self-assembly. We're particularly interested in compounds which are photoexcited. And the aim of the work is usually to make sensors or probes for anion, bioanions, biomolecules, things like this. So that kind of leads to things like cell probes or even therapeutics, or to be more trendy, an area called theranostics, which is, diagnostics and therapy all rolled into one. My philosophy is I don't like making things just for making things, so I do like to make things for some reason. So I'd like to think that in long term we could, contribute to producing something that makes a difference for instance, in treating cancers or something like this. I mean, we have got some compounds which, if you've asked me 20 years ago, I wouldn't believe this, but we've got some compounds now which are beginning to get to the point where they're going to be tested with animal models and things like this. So, so they are actually genuinely therapeutic leads. And we've got some interesting compounds which could perhaps be used for diagnostics. So you could use them for detecting certain cancers early. The treatment success for cancer, if you pick up, say, something like breast cancer early, there's over a 90% success rate of treatment over 5 years. Whereas if you don't, it's 85% of people die. And it's even worse if you take something like ovarian cancer. So ovarian cancer, if it's not detected early, then there's a 5% survival rate. And it's over 90% if it's detected early. So we're quite interested in, diagnostics as well. I mean, if we could produce something for that, I'd be really happy. There's kind of two ends to it, really. We've got one set of systems which are based on self-assembling quite big structures, architectures, which can be used to bind to DNA or other bioanions in unusual ways. So like, for instance, we've got one system that self-assembles and it kind of binds to DNA in a way that only one other thing binds to DNA that way, and that's a transcription factor which is involved in reading DNA when it's converted into RNA. So that's quite interesting. And then on the other side of things, we're making very simple substrates that bind to those kind of DNA structures that duplex DNA very simply through stacking between the bases and things like this. And some of those are just for visualizing DNA within cells and things like that, and some of them have been designed so that they're either intrinsically cytotoxic, so that they're not only can you see them, but they damage DNA in a way that produces a therapeutic effect. I did this thing about science meets art. This is the mini version of it. Okay, so you can see it's actually real origami. Okay, so it's based on one of our complexes bound to DNA. But this toured this was toured Sheffield, like in community centres, and the last place it was in was a medical school. They were going to throw it out, so I thought I'll have it. Yeah, it's very interesting. My take on it is that biology is becoming more and more chemistry, actually. All right, it's essentially molecular biology is just the biological chemistry of cells. Yeah. And it's easier to be a chemist to move into biology than it is a biologist to move into chemistry, because chemistry is a more fundamental subject. It's dare I say it, more rigorous. So you need to have a very good molecular understanding before you can move into things like cell biology at that level. And to many biologists, not all, but many biologists, chemistry is like a black box. And to understand things like how CRISPR works, needs to really understand things like molecular recognition, how the molecules align and recognise each other. And so I think, chemistry will have a lot to say in the way that cell biology, molecular biology is developing. You have to be scientifically literate to be able to assess the arguments which are taking place in public about this issue, and I would argue it's probably one of the most important issues globally at the moment. And for various reasons, there are lots of people who have got opinions on this who perhaps are ill-informed, poorly informed, or I would argue actually purposely going around trying to disinform people. So I think it's important that people have an understanding of being able to assess data, not just on who shouts the loudest, but actually from evidence. And so I think it's important that students, just this is a general thing, not on my course, but a general thing that students are, one of the important things about science is it's basically codified common sense. Okay, what it's about is trying to be objective, look at the evidence and try to come up with a model that fits the evidence, and opinion should have as little as possible to do with it actually. So things like environmental chemistry are important areas where that kind of Occam's razor approach should be developed, and I think perhaps sometimes it isn't. It's rewarding, it's creative, I hope you're doing something, well hopefully you've signed up for a project that you find interesting, so you're basically doing something that you like, but 9 to 5, you get paid for it, and it engages you mentally, and it's very different from being an undergraduate, because as an undergraduate obviously you need to learn the basics of chemistry to be able to move forward, to be actually do research. But research is a very different process to just learning about science. It's the difference. You actually become actively doing science, and so that's a much more, in my opinion anyway, it's a much more engaging process than sitting down and learning a lot. But like if you want to read a book, you have to learn the alphabet. So there's always tough stuff to do before you can do the really interesting thing. If you want a job in most of the chemical pharmaceutical industries, it makes a big difference if you've got a PhD. One thing is that quite often people don't realise that how international research science is, and how all the people in this department have an international reputation. If you were to go to Germany and mention some names, of people working in Sheffield, people would know them. And the other side of that coin is that if you are working in research, it is in an international community, so you do get to travel a lot, and you will have people from all around the world working in labs, and you may find yourself somewhere else in the world working with lots of different people. So a PhD can be a passport to international travel as well.